Hi guys, it's Mrs. Lapola. Welcome to my first video, my first mini vignette from chapter 7. This is going to be a little bit of a review on how to use solubility rules and predicting double displacement reactions. So to do these two problems that we're going to do in this little video, you'll need to make sure you have these. Let me get my pen here. You need to make sure you have these solubility rules in front of you. They are from the PowerPoints that you can print out. You'll be able to use them on quizzes and exams. There's also a copy in your textbook. But you'll need these solubility rules along with a periodic table to correctly predict products from double displacement reactions. So just a reminder of how to use these solubility rules. The way that this chart is organized is that species that are in this region where it says if they are mostly soluble, that means that species dissociates into its cations and anions in aqueous solution. So things that are mostly soluble have this state of AQ, aqueous. If something is insoluble, if it falls in this category, right? If it falls in this category, that means that that species does not break up into its cations and anions in solution. They stay together as a solid. Therefore, things that are insoluble have the state of S for solid. Okay? So remember that and have your solubility rules in front of you when we do talk about these next two examples. So we did this example in class before break, but I'd like to go over it again just to review some concepts of how to predict double displacement reactions. So if you remember, in double displacement reactions, you have two ionic compounds. In this case, we're going to have them be AB and CD, where the first is the cation or the positive charge, and the second is the anion or the negative charge. And in a double displacement reaction, the cation of one species pairs with the anion of another species and vice versa. So in this AB plus CD reaction, the products for it would be AD and CB. Now make sure when you write those products that you always have the positively charged species first and the negatively charged species second. Also, when you put those ions together to form a neutral compound, you need to make sure that the charge is balanced. So let's review this example that we did before break. So in this example, we have sodium carbonate that is aqueous reacting with copper 2 chloride that is also aqueous, and we want to know what the products of this double displacement reaction is. Okay. So in this little cartoon that's listed, we already have the arrows kind of showing you the crisscross or the switching of ions, the switching of pairs of ions to give you the products. But I think it could be instructive, and in fact, I recommend that you do this. I recommend you do this little crisscross and write down what the cation and the anion of each species is, and then you can easily see what your crisscross is for your final products. So for example, sodium carbonate. What is the cation or the positively charged species of that molecule? Well, the cation is sodium, Na, and it's not Na2. This 2 here in the reactant is just to balance the charge of sodium in that overall molecule. The cation is just sodium, and since sodium's in group 1, it has a positive 1. The anion is carbonate. It's one of those groupies that you had to memorize, CO3. 3 is prior to the groupie, it comes along for the ride. Carbonate has a negative 2 charge. So that is the cation and anion for sodium carbonate. Now let's go to our second species, copper 2 chloride, and write down its cation and anion. The cation is copper, Cu. Copper is one of those species that can form multiple charges. It's a transition metal. But looking at the formula for copper 2 chloride, I know it's +2. How do I know that? Because when I look at the chlorine, that is the anion, I see that there's 2 of them in that molecule. Each chlorine is a -1, and if there's 2 of them there, that means the copper must be a +2. Okay? So that's why copper is +2. That is the cation. The anion is chlorine, which is a -1. So now we have our crisscross set up similarly, kind of like A, B, C, D. And I like this crisscross method because you can easily see the charges and what pairs with what. So what is the products going to be for this double displacement reaction of sodium carbonate and copper 2 chloride? Well, my products are going to be NaCl, NaCl. That's one product. The second product is going to be copper carbonate. And since copper is a +2 in this case, carbonate's a -2, I just need 1 copper and 1 carbonate. So those are the products from this double displacement reaction. So in my little flow chart here of steps, we've predicted the products. We've made sure the products are neutral, meaning cation and anion charge added together equals 0. Now we need to make sure that the equation is balanced. Remember, balanced chemical equations have to have the same number and type of atom on the left equal to the number and type of atom on the right. Comparing the reactants, sodium carbonate and copper 2 chloride, with your products, you can easily see that the sodiums are not balanced. I have 2 sodiums in my reactants. I only have 1 sodium on my product side. So the only way to change the number of sodiums on my product side is to add coefficients in front of the molecule. So in this case, I'm going to add a, I'm going to add a 2. I'm not sure why I went back. Sorry, guys. There we go. So putting a 2 there, I now have 2 sodiums. And that works out great because when I put that 2 there, I now have 2 chlorines. And how many chlorines do I have on the right-hand side? Or on my reactant side? I have 2. I have 1 carbonate on my reactant side, 1 on my product side, 1 copper, so I now have a balanced chemical equation. Remember, when balancing chemical equations, number and type of atom have to equal number of type of atom on both sides, on the left and on the right. The only way that you can do that is by adding coefficients, numbers in front of the molecule. Next thing we're going to do is determine the states of our products by using those solubility rules. And you should be able to see that sodium chloride is aqueous according to those rules, and copper 2 carbonate is a solid. Okay. So we now have a balanced double displacement reaction. And that's where we left off before spring break. Let's try those same rules again with another example. And on this example, I gave you a little bit of a hint here. I already gave you the coefficients of the molecules of the reactants. But let's say I was to give you these 2 reactants, potassium phosphate, aqueous, reacting with nickel 2 chloride. And I want to know what the products of that double displacement reaction are. So I'm going to go ahead and do my little crisscross again. In the first reactant, potassium phosphate, my cation is potassium, which is a +1. I didn't put K3 here. Remember, that 3 is just there to balance the charge. The actual cation is potassium, which is a +1. The anion is phosphate. It's a groupie you needed to memorize. Phosphate is a -3 charge. Nickel is the second cation. It's going to have a +2 charge. And I know that because in my nickel chloride, I have 2 chlorines. Each chlorine is a -1. And since there's 2 of them in that molecule, my nickel must be a +2. So I've written my little crisscross up here so I can clearly see the cation of one pairing with the anion of the other. And when I do that, I see that my potassium is going to pair with my chlorine. And I'm going to need one of each because potassium's a +1, chlorine is a -1. For my second product, the nickel is going to go with the phosphate, but I can see that nickel, since nickel's a +2, and my phosphate, I know, is a -3. When I put those ions together to form a balanced molecule, I can't just use one of each to get the charges to equal the same. I need to do the little crisscross here of the charges so that the charge, numerical charge on one becomes the subscript of the other. So my product is going to be Ni subscript 3, and then PO4. And how many phosphates, how many PO4s do I need? I need 2 of them. And since I need more than one of the polyatomic, I have to use parentheses and a subscript. So those are the 2 products of this balance. These are the 2 products of this double displacement reaction. Is the reaction balanced? Well, like I said, I gave you a hint over here. I put that 2 there. Right now I have 6 potassiums on my reactant side, and I've only got 1 potassium on my product side. So the only thing I can do is to add a 6 out front. Now I will have 6 potassiums. And that works out great because I have 6 potassiums. I also have 6 chlorines. Hey, on my reactant side, how many chlorines do I have? I have 3 times 2 or 6. So that looks good. I have 3 nickels on the right-hand side. I have 3 on the left-hand side. I have 2 phosphates on the right-hand side. I have 2 PO4s on the left-hand side. So we now have a balanced chemical equation. The only thing that's left to do is to use our solubility rules to determine the states. And you should be able to see that potassium chloride is aqueous. Believe it or not, that's an A. And the nickel phosphate is a solid. So that is the products, balanced products with states of this double displacement reaction that is written more neatly right here. So we're going to talk about in the next video how we take these molecular double displacement reactions and write them into something that's useful for chemists that are called ionic, total ionic, and net ionic equations. But for right now, for this video, we're going to stop here with this molecular equation. And it's called molecular because you can see all the reactants and all the products are written as intact neutral molecules. It shows the complete neutral formulas for every compound in this double displacement reaction.